Howdy, my name is Jacob Hartzer. I'm a graduate student in mechanical engineering at Texas A&M University, and today I am here on behalf of the Unmanned Systems Lab to give a presentation entitled AutoCone, an omnidirectional robot for lane-level cone placement. In this presentation, I will cover the background and problem, the system architecture, kinematics for the omnidirectional cone, filtering for the state estimate, and the results of our experiments. First, I would like to introduce the motivation for us to look into this problem. In the United States from 2011 to 2017, transportation events caused 76% of roadway work zone fatalities, and in 60% of these events, the worker was struck by a vehicle in the work zone. Generally, to improve worker safety, traffic control devices should be used, and these include signage, barrels, or cone delineators. However, the act of placing the control devices themselves is dangerous, and temporary structures are hard to implement. Therefore, we are seeking a method to automatically deploy cones from a work vehicle. From this information, we formulated the following problem. The system must place 3 cones in 40-foot increments in this triangular wedge shape, where the wedge begins 80 feet from the end of the vehicle. Additionally, the cone placement device should operate on highway surfaces and be unaffected by small debris. The cone placement device should remain within the lane despite road curvature to avoid being hit by oncoming traffic. Additionally, we don't want to rely on road-embedded sensors, as this would be difficult to deploy quickly and with low cost. Finally, we would like the units to cost less than $1,500 each due to the high likelihood that they will be struck by oncoming traffic. In selecting a platform for the system, there were many different design considerations. Cost was a major factor and led to many of our design selections. We wanted the system to be holonomic to allow the system to move in any direction. This makes operator initialization error easily correctable, while also giving the robot more adaptability in its motion. If obstacles were detected, the desired path would be easily correctable while remaining within the road lane. To achieve holonomy, we explored the use of 3-wheeled Omni systems and 4-wheeled mechanism systems. Because Omni systems would require one fewer motor, a 3-wheeled Omni system from Superdroid Robotics was selected. We specifically sought out a system that had encoders on its motors to aid in our dead reckoning in case GPS signal was lost. A major driver for this project was the release of the new RTK GPSs, which have really expanded the realm of high accuracy and low cost positioning. Without it, we would not likely be able to develop the platform for as low of a cost as we would like while still achieving the same level of positioning that is needed. Additional sensors were considered. LiDAR was considered but not used because it would be cost prohibitive, and cameras were considered but not used because we found that in the environments that we would be operating in, there were not consistent lane lines to actually navigate off of. Additionally, imperfections and inconsistencies in the road surface made it difficult to reliably use cameras at all times of day and night. The resultant platform is a omnidirectional base controlled by a Raspberry Pi. Feedback is given via the motor encoders, and measurements are taken from a RTK GPS. In designing the system architecture, we took a very user-centered approach. We wanted to be able to control the deployment and retrieval from a base station, and to achieve this, each cone runs a ROS core, and the Nimbro network package is used to pass state information between the cones. This information is used to avoid collisions, but in the future we would like to use this information in collaborative localization of the cones. So, the central computer sends commands to deploy and return, while each cone calculates its own path information. Additionally, each cone receives correction messages from a RTK base station to greatly increase the accuracy of the onboard GPS. Because the system is holonomic, it is relatively straightforward to control. We can independently control all 3 degrees of freedom of the system, and pictured on this slide is the forward kinematics derivation for the cones. In implementing a Kalman filter on the cones, we wanted to utilize the information that we have from the forward kinematic derivation as well as the motor encoders. And so we decided to go with an extended Kalman filter where we could use the forward kinematic information as our prediction equation. Additionally, the measurement updates are given by the RTK GPS with corrections. Beyond that, the standard extended Kalman filter equations were used. In the development and testing of this platform, we used 2 different control schema. The first being proportional control, which only utilized position error. This completely ignores any kind of path information, and while being much simpler to use, is affected by motor spool up and spool down. This produced a half-meter maximum error in our box test shown to the right, which mostly was caused by the spool up pushing the system to one side and not being able to correct its heading and position until much closer to its final destination. After seeing these errors, we implemented a kinematic control schema. This incorporates the path information, which allows us to reduce the lateral errors. In this case, we saw a 0.2 meter overshoot, and we're actually able to reduce these overshoot errors by tuning the kinematic controller and taking into account curvature information of the path. Having shown that the system was able to accurately and repeatably place the cones using these RTK GPSs in an open environment, we knew that it would be important to test it in more constrained environments. So on the highway, GPS is not always available. An example of these places are in overpasses and bridges, which can obscure or completely block the GPS constellation. Therefore, the system must rely on dead reckoning and would be subject to drift. When we tested the proportional control schema in this environment, we saw how susceptible it was to GPS errors, with a maximum positioning error of almost 8 meters. However, the kinematic control schema performed much better. While even receiving poor GPS data, it performed well. The system remained within the width of a lane line throughout its deployment and achieved a maximum error of under 2 meters. Shown here is a video of the cones being deployed. What is currently being done is the kill command is being turned off, so then the cones will actually start to deploy. The first one moves until it is outside of the collision detection zone of the second because of that state information sharing we discussed earlier, and then they proceed to follow their path out to their desired location. In this case, we are just giving them points that are 5 and 10 meters out, and so that's why they're just simply traveling in a straight line. And they will idle until the return command is sent, and once that is, then they will both start to come back along the same path that they originally took. All the while, they are making sure that they are not going to collide with each other, and they're doing their best to come back to not only the same location, but follow the same path. And so this will allow for easy deployment and retrieval. And as shown, they come right back to where they started. In the future, there are a number of improvements we would like to make for the cones. First would be improving the localization accuracy of the systems. To do this, we are considering adding ultra-wideband ranging modules. This would allow the cones to range not only between each other and collaboratively localize, but also between a possible landmark on the home vehicle itself or highway infrastructure. Additionally, we would like to incorporate lanelet information for improved path data. We could pull this information from a source such as OpenMapBox, and this would allow the systems to not only calculate paths on the fly, but also to be aware of which particular lane they are in. Once implemented, we believe that these improvements move the platform much closer to a commercially viable product, as is the eventual goal for these systems. In conclusion, the team was able to develop a system that only costs $1,600 per unit and is operable on highway surfaces. Additionally, the system is not subject to operator initialization error and has shown that lane level wedge placement is achievable. The system has shown that multi-robot coordination is possible and has achieved less than half of a meter in RMS error in GPS denied environments. Beyond this, we see much higher localization accuracy when there is a full GPS constellation available. And as such, we believe that this platform is extremely viable for the given problem. And we very much look forward to continue this research to see how we can apply these platforms to future road safety applications. This concludes the presentation. Thank you so much for your time and for your attention. And I welcome you to reach out if you have any questions. Thank you.